Could you tell us how much it would have cost to put in? Are we talking 10 cents?
No, we're talking dollars. I think we're talking dollars.
Right, so that's what an expensive part.
Yeah, I mean, when Nokia do pricing of Nokia did do pricing of phones, I should reiterate. They used to just measure the silicon area and say they just used to pay by the area of the silicon in the chip. That was the price they paid. The IP in there, they weren't interested. They just measured the size of the die. Yeah. That's what it costs you to fab it. Here's your profit. That's what we'll pay for it. And so it was quite a big piece of silicon, quite complicated. Did more than we needed it to do, because we don't, on Raspberry Pi there was really no concept to start powering a lot of stuff down if we didn't need it. Yeah. Because invariably we were going to be running the HDMI, so we needed it. So you end up with this great morass of power supplies that you've got to manage, and of course that was, to my chagrin, my downfall on the prototype, in that I think it was SD-RAM VDD, I can't remember exactly, that's the one I didn't connect. It needed to be connected to 3V, to the 3V3, and I didn't. So we have all these sort of things. So we've got a full array of BGA boards, just to try and put that in context. We talk about this thing called BGA fan-out, and it's actually the only complicated thing on the Raspberry Pi. Everything else is fairly straightforward. So you've got these. Is everybody familiar with what BGA is in terms of it's the connections? So the connections to the chip are in a grid on the underside of the device. Okay. Now, Intel used to make chips where if you turn them over and it just looked like a load of cones because there was a lot of pins coming up. They were a pin grid array. This is a ball grid array, so instead of being pins, it's little solder balls. So the underside of the chip just looks like a set of cannonballs, basically, arranged in an orthogonal array. And what you do is you turn it upside down, you put it through an oven, and those balls melt and connect it to pads on the board. I mean, I can talk more about that offline if anybody wants to know, but basically, the important thing is they come in this geometry of an XY array. So if you're going to try and get all the signals out of here, then you can have one layer of your circuit board and you can get 2 rows of those out. That's fine. You can now be a bit tricky and you can add vias. So these are the balls of the device and these are things that go through the PCB. Okay? Sorry, I did say it might get a little bit geeky. Then to get those out, you can actually wire 2 more sets of tracks. Okay, that works. So I've got the 2 layers, I've got 4 of my rows of balls coming out. The 5 rows, I can only get 1 out then because I've got to miss these things that go all the way through the board. And it just gets worse. So on a 19 by 19, you can see I've got quite a challenge to try and get all these tracks to escape from that grid in the minimum number of layers.
Why couldn't you sort of get them out upwards and sideways?
Well, you can, but don't forget that this is just sort of like a small sample, and this device has got 19, right? So I've just sort of picked the core of it. But you're right, if we get devices that are just 3 by 3, yeah, then you can get them all out easily. Then it's 4 by 4, it's not quite so easy. 5 by 5, it gets a little bit more difficult. I mean, we actually routinely deal with devices that are, I can't do the maths because it's, there are 1,154 pins on it. So they're absolutely humongous. And so you have to have a strategy for getting things out. It turns out it's not quite that bad. But essentially, how it works out is that you need 7 layers on a PCB to get every single one of those balls out separately. And we just couldn't afford that. We were going to be stuck at 6 as an absolute maximum, and we had to have all the power supply connections in. But the thing we noticed is that the Broadcom requirement is that all the decoupling components, i.e. all the things that keep the power supplies smooth, have to be underneath the device. I was talking earlier about EMC. In order to keep the EMC down, you have to have that cluster really tight and close. And so we were quite lucky in that 70 of our 299 pins are actually connected to ground, because you do need quite a solid connection for these chips to ground for them to work properly. And what we realised is we could use a trick which is called an L1 to L2 blind fire, and I'll show you what that is because it probably means nothing to those people. So this is our BGA, which is our chip on the top. These are the solder balls that actually connect it to the PCB. This is like a connection on the PCB, which we call a fire, that allows you to connect from one layer to another. Then there's a sneaky little one where you just drill it all the way through the board, so that only connects to this layer here. But the beauty about that is it gives you space on the bottom of the board to add chips. So by using a combination of blind and through vias, we were able to get all the parts underneath the Broadcom chip where they needed to be. I completely baffled everybody.
Is it worth pointing out that's a cross section?
Yeah, it is a cross section. Sorry, yeah, cross section through the board. Yeah, good point. Because normally a wire is drilled all the way through with a high-speed drill, but these are just drilled with a high-speed drill. It just stops when it gets a small way through the board.
Presumably that increases your board fabrication cost.
It does fractionally. In fact, in volume production, you put those in with a laser. It takes about half a second to laser a platter of 6 Raspberry Pis. It's just done. Move to the next one. And the cost is actually the labour of pushing the boards through the machine. It gets more complicated. If you then decide to do the bottom as well, then increase cost. Interestingly, we have found, that we can reduce the cost of the board by taking them off, because there are other processing steps about the copper build-up that actually do add cost. And there is a 10 cents benefit, something like that, if we can get rid of them. And so, know that there's a 10 cents benefit to get rid of them. One of my engineers then sat there in the evenings for 3 weeks to prove it could be done without blind vias. And we produced another design just to show it could be done. But because we'd already implemented it, it really wasn't worth moving to it. But he tried to prove that he was a better PCB layout designer than me. But then I had a big argument about where he'd moved some of the components that were underneath to. Oh, it's all a trade-off. Everything about designing something like Raspberry Pi is a trade-off. It's a question of trying to balance all those knife-edge decisions such that you get it as right as you can. So this is just an example where this little 1-2 symbol just indicates that wire is only going to go through the first 2 layers. These are the actual pads where the Broadcom chip lands. And these in purple are actually components on the opposite side of the board. So there's one there, there's one there, there's one there, and the one there. There's quite a lot of stuff on the back of the board that we had to get in. When it came to sort the power out, I just resorted to the old technique.
That's what we like to see.
Yeah, what, the old technique?
Yeah.
Oh, this
Understand that one.
this was just the 3 services to the 3 houses problem. You know the one?
Yeah.
You know, you give it to the kids and they spend hours and hours trying to do it, and it's actually impossible. This is, in essence...
I found a way of doing it.
Sorry?
I found a way of doing it.
Fold the
There's
paper.
2 ways to do it. You either fold the paper or you draw another electricity.
Yeah, so we're now going to go in for curved printed circuit boards on the next Raspberry Pi. In essence, what I was trying to do, when my dad was an electrician, so he always taught me about ring mains, that they can carry better power than anything else. So each one of the power circuits, as far as I could figure it, is done as a ring main. The little dotted lines is where I had to admit defeat and hop it to another layer to get the bridge over. But in essence, those are the 2 layers that contain all the power. Of course, as it turned out, because I thought one of these was separate, I actually had one more than I needed. And having one less would have made that infinitely easier. But hey, you live and learn. So I used that to actually figure it out. I actually drew these out. I think I printed about 50 sets of these sheets, and then took them on the train to Edinburgh, and sat there with my pens on the train trying to figure it out. And was determined to get it sorted before I got to Edinburgh, which I managed to do. I managed to find a fairly optimal way of doing it. The other thing that's slightly unclear from this is that you can't get power between these rows. So the two pads are actually adjacent. You can't get anything in between, although it looks as though you can, because it's so microscopically thin it won't carry any current. So let's just have a little bit of a look around the board. So I say that the board is basically quite simple, but it has a few tricky things you need to worry about. And one of the things is the HDMI. So HDMI principally runs at gigabit speeds. That's how you're able to get such high definition video with such a small number of channels. And it uses a thing called differential signalling. Does that lose most people if I say differential signalling? Yeah, maybe. In essence, what you have is two signals. And what you do is you go, that's one, and that's a zero. In a normal signalling system, you just do it like this. But you have these two signals that do that. Now, the beauty about having two signals that do that is that they actually don't actually offend the local area, because they cancel each other out, or at least they're supposed to. But the requirement for that cancelling out to work correctly, so you don't get any radiation off the signals, is that they're travelling at the same speed and they're next to each other. And so what you end up having to do is, as they come out of this chip, we end up having to put these wiggles in to make the length of these tracks here exactly the same. So when you get them to this point here, the distance from that pad to there and the distance from that pad to there are exactly the same to 0.1 of a millimetre. That means that the two signals will arrive at that chip exactly together, doing that or doing that. And what that does is it massively reduces the radiation from those tracks and from those signals going out of the board. And it's been used for years. I mean, RS422 is exactly the same principle of differential signalling. And if you keep those cores on the twisted pair, you will reduce the radiation from that 422 signal. We had to do something similar for the Ethernet to keep the tracks tight and together. And this here is the USB, which again we keep tight. One of the massive benefits of Raspberry Pi is it's small. So these tracks are not running for miles across boards. And so it's actually relatively easy to get what we need. If you actually look at the whole thing with Raspberry Pi, this is the bottom layer of Raspberry Pi that we all see. And really everything's going on, this is my opinion, everything really goes on in that sort of red area which is underneath the chip. If you actually look inside, these layers here, but where we've got these ring mains of power, you can just about see one going around here. It sort of stops there and goes back around. That's because it's linked over on another layer to actually make that bridge to make a ring of power supply. These are the main power supplies coming in down here. And this little bit here is where the on-chip power supply is for the Raspberry Pi. If you look further through, this is what I call the cheat layer, where you really couldn't get all the signals in. We've got some of the signals on here. We've got some of the bridging power on there. Most of it is filled with ground. Because ground layers help to keep the board stable electrically. And then that's another power layer. And that is the true ground layer of the board. So that crucially is the ground reference for everything on the board, which is why all the signals that have to be differential and what we call controlled impedance are actually on the top layer. And so the reference between layer 1 and layer 2 is very carefully controlled. Do people know about reflections in signals? Basically, you must have seen that if you when you used to have old video monitors where you have a 75 ohm termination and you forget it, you get these funny ghosts appearing on, and that's because the signal ends up coming to the monitor on a 75 ohm cable. It sees an open circuit. That then causes the signal to double and also get transmitted right back down to the other end of the cable where it came from. And when it gets there, it gets reflected back. And because of the time it takes to do that, you end up with all these ghosts. So you get this absolutely horrid picture. But if you terminate it in 75 ohms, all the signal just goes straight down there and you get a nice clean signal. So the theory is you're always supposed to terminate everything in the same impedance as the conductor that carried the signal. There's a couple of other ways you can do it, which of course if you come on the computer science course at Manchester, you can get talk about it, I think, still.
No, that's
We don't do
hardware.
it. That's hardware, all right, we don't do anything.